Hi everyone. In this next lab, we're going to be dealing with very basic circuits. We're going to be testing an incredibly important equation in circuits. One of the most basic but most useful circuit equations, which is called Ohm's law. Ohm's law says that the current through any device is equal to the voltage across the device divided by the device's resistance. And we'll see a little bit later that Ohm's law doesn't apply in all situations, but in a lot of very important ones, it does. As we're going to be verifying in this lab and testing it out on a couple of resistors. So Ohm's law relates three things: voltage, current, and resistance that we don't yet have any context for. We'll be talking about voltage very shortly. Then we'll be talking about currents and resistance together at the start of the chapter on circuits. So for right now, we're just going to have sort of a crash course on these three concepts. You don't need to fully understand them yet. You just need sort of the basics to get through this lab. And then we'll return to these concepts later. So it's going to be kind of a preview, kind of a taste of circuits before we return to them later. It's part of giving you sort of multiple exposures to the same material so that you can retain it better. So let's start out with voltage, which is written using delta V generally. So when we talked about electric field, one of the things we said about electric field was that it told you what force a charge would feel at a certain point in space if there were a charge there. And we defined it using a test charge or a probe charge. Voltage is very similar in a lot of ways, except that instead of having to do with electric force, it has to do with electric potential energy, which we'll define shortly. And voltage determines how much a charge's electric potential energy would change if it moved between 2 points. The details are not really important right now, but voltage is defined between any 2 points in space. It's measured in standard units of voltage, which confusingly is also written with a capital V. And the job of batteries and other voltage sources is to maintain a voltage between their terminals. Different devices will maintain different voltages. A AA or AAA battery will maintain 1.5 volts between its terminals. A 9-volt battery will maintain 9 volts. Standard wall sockets in the United States maintain 120 volts between their terminals, while the third prong is grounded. Talk a bit more about that a little later. The voltage sources we're going to be using in this lab are variable voltage sources, which have a knob on the side that you can turn to increase or decrease the voltage they maintain. Also, in working with circuits, when we draw circuits, we use standard symbols that identify the type of circuit element that's being drawn. And a voltage source is represented by either a set of 2 parallel lines within a circuit that have unequal lengths, or a set of 4 parallel lines with unequal lengths. Either one is acceptable. So that's voltage. Current is quite different. Current is represented by a capital I. Capital C is already used for something else, unfortunately. I don't know why I is the symbol they landed on. But current is a rate of flow of electric charge. So far, we've been talking about situations where electric charge is largely stationary, or electrostatic situations. In circuits, electric charge is moving and flowing. These are electrodynamic situations. So current is a rate. It's a rate of flow of electric charge, technically defined as the amount of charge flowing past a single point per unit time. And current is defined as the time derivative of charge past a certain point or past a certain plane in a conductor with respect to time. Standard units of current are amperes, or as almost everybody says, amps, is represented by a capital A. And it's found experimentally that if you apply a voltage across any conductor, it'll cause charges to move through that conductor and therefore cause a flow of current. If you double the voltage, you double the current. And so there's a direct relationship between the current through any device or any component and the voltage across that device or components. So if you apply a voltage across a conductor like this, current will begin to flow through it, and the amount of current will be proportional to the voltage. But to make that proportionality into an equality, we need one more concept, which is resistance, represented by an uppercase R. Resistance tells us how much a given conductor inhibits the motion of electrons, or the flow of charge, through itself. It has standard units of ohms, which are written using the Greek letter omega, which sounds like ohm conveniently. And in a circuit, a resistance of any kind is represented by a jagged set of lines, like this. Certain devices are specially designed to be used in circuits as a way to inhibit the flow of current in certain regions. They're designed to have a very, very specific resistance. These are called resistors. And we're going to be working with some of them in lab today. So you'll see resistors represented by these sets of jagged lines in a circuit diagram, but also any sort of resistance in a circuit is represented by these jagged lines. That might be resistance in wires, or resistance in a voltage source, or resistance in some device. That's always represented by these sets of jagged lines. So resistors are very carefully machined to have very specific resistances to the flow of current. And resistors come in many different values, many different types. And generally, the value of a resistor's resistance, is sort of written out on the outside of the resistor. But it's not actually written out using numbers and units. Instead, I guess for easier printing, it's written out using these colored bands. There are generally 4 colored bands on a resistor. It looks something like this. And there's a very specific way of reading them. And there's a table on the last page of this lab that shows you how to read off those resistance values. But I wanted to do just a quick tutorial here. So there are generally 4 bands. One of them is offset from the rest. That's the 4th band. It only has a limited possible set of colors. So the first band on a resistor tells you the first digit of its resistance. That depends on the color of the band. Green is 5, blue is 6, red is 2, and so on. There are various different colors representing different numbers. The second band is the second digit. So by reading off the first 2 bands, you have a 2-digit number. And the third band is a multiplier that you multiply that number by to get your final nominal resistance. That's the resistance that the resistor is designed to have. So one band corresponds to multiplying by 10 to the 0. We're just multiplying by 1. One corresponds to multiplying by 10 to the 1st. One color to multiplying by 10 to the 2nd, and so on. So to get the nominal resistance value, you read off those first 2 bands with colors corresponding to digits. That'll give you a 2-digit number. And then you multiply it by 10 to some power. And that power is given by the 3rd band. Finally, the 4th band is the tolerance. It's essentially how precisely the resistor was machined. It gives you a percentage uncertainty of the resistance value. So it essentially tells you how well you can trust that particular resistor to have something close to its nominal value. So just to recap, if we wanted to read off the value of this resistor here, which has a green, blue, red, and then gold band. First, we'd read the first band. That's a green band. We can look at our table and see that corresponds to a 5. Then we read the second band. It's a blue band. We can look at our table, see that it corresponds to a 6. And finally, we read off the red band and see that a red band as the third band corresponds to multiplying by 10 to the second, or multiplying by 100. So we take 56 and multiply it by 100. We get a nominal resistance of 5,600 ohms. To find the uncertainty in that value, we look at the tolerance. We see that a gold band on our table corresponds to a 5% tolerance, and 5% of 5,600 is 260 ohms. That means that the range of possible resistance values for this resistor is 560 plus or minus 280 ohms. So plugging in those numbers down here, and noticing that we have two significant figures from the, we have 3 digits before the decimal place. This rounds to roughly 530 to 590 ohms. Okay, so voltage causes charges to move and therefore creates current. Resistance resists the flow of electrons and therefore inhibits current. And putting those together gives us Ohm's law, which again says that the current through any device should be equal to the voltage across that device divided by its resistance. So we'll be again verifying Ohm's law in today's lab. And later on, we'll sort of return to this topic, and we'll see that there are some devices that don't follow Ohm's law. We call those non-ohmic devices. So in today's lab, we'll be essentially working with the most basic possible circuit, which is a voltage source connected by wires. I've drawn wires in green because they are conductors, to a resistor. Single resistor. And as it turns out, there are two sort of main ways to connect components within a circuit. The first way is called connecting devices in series. When you connect two devices in series, like these resistors here, the front of one device is connected directly to the back of the other device, so that they're in essentially a single line. They can actually wrap around corners. All that really matters is how they're relatively connected to each other. And when two devices are in series, any charge that moves through one device also moves through the other device, which means that the current is the same through each device or each component in series. The other way to connect components is to connect them in parallel. When two devices are connected in parallel, the front ends of the devices are connected to one another and the back ends are connected to one another. So they share the same set of wires on the front and they share the same set of wires on the back. And because voltages are across devices, if you have two devices in parallel, then both of them will have the same voltage across them. And we're going to use this knowledge of how devices can connect in either series or parallel, and what that does to the voltage and current, to make use of measuring devices, to measure current and voltage. In actuality, we'll be using multimeters for both, which can change from a voltmeter to an ammeter using a knob. We'll have one of them be a dedicated voltmeter and one be a dedicated ammeter. So an ammeter is a device used to measure current. And what an ammeter is actually measuring is the current through itself. It has two leads on its ends. And when current flows in one lead and out the other, the ammeter measures the current that flows through itself. And because it's measuring current through itself, the best way to use an ammeter to measure the current through a given component is to place the ammeter in series with that component. A voltmeter works somewhat differently. A voltmeter also has two leads, but instead of measuring anything passing through those two leads, a voltmeter measures the voltage across those two leads. And therefore, what it's actually measuring is the voltage across itself. And so you want to use a voltmeter to measure the voltage across a certain device. You want to place that voltmeter in parallel across that device. So with that in mind, we can think about the circuit we're going to be using for today's lab, which is essentially that most basic circuit, but with a voltmeter and ammeter being used to measure the current through and voltage across a resistor. So we have a power supply. It's actually a variable power supply whose voltage we can change. We're going to be changing it to specific values, measuring that voltage, and then measuring current through a resistor. We have an ammeter, which, if it weren't for the presence of this voltmeter, would be directly in series with our resistor. That can be used to measure the current passing through that resistor. And we have the voltmeter, which is directly in parallel with our resistor. So we're going to be using this basic circuit here to measure voltage and currents of a resistor, various different voltage values. We're going to be using Excel a little bit to graph those values and see if we get a linear relationship, which will help us find the resistance of these resistors. All right, I'll see you all in lab.